Welcome to Chapter 2 on polynomial power and rational functions. We begin by defining a polynomial function, followed by an in-depth analysis of linear and quadratic functions. And a polynomial function here, we have this definition of a polynomial function, and it looks pretty intimidating, this equation, but it's not so bad. It is defined as a function where the variable x has a whole number exponent and a non-zero coefficient a sub n. The standard form lists the variable with the largest exponent first, so this would be the x variable that has the highest power comes first, and then the rest follow in descending order. That's n minus 1, n minus 2, and so on. N is actually called the degree. It's a whole number. A sub n is just a number. It's a coefficient in front of our variable x, and it is called the leading coefficient. So one of the things you're going to be doing is identifying polynomial functions and listing their degree and their leading coefficients. So here's an example down here where we have 3x minus 5x squared. Well, this term has the highest power. It is a polynomial equation or a polynomial function. So the degree number would be 2 and the leading coefficient would be negative 5. So we would list this term first followed by the x term. So those are in reverse order. We would put those in standard form before we identified that. Our second example, h of x, is not a function because if we were to write that in exponential form, that would be x squared minus 4, the quantity. The square root is actually to the 1/2 power, so that is why that one is not a polynomial function, because it has a fractional exponent. S of t, this is a polynomial function. It is in descending order or standard form, so we would say its degree is 4 and its leading coefficient is 2. G of x equals 6 is also a polynomial function. Its degree is 0 and its leading coefficient is 6. And the last function on the right-hand side is not a polynomial function because it has a fractional exponent. So now that you recognize and can identify leading coefficients and the degrees of some polynomial functions, let's go ahead and look at some polynomial functions that have special names for them. And we will start with the zero function. The zero function has an undefined degree, and the zero function is just f of x equals 0. The next function above that is the constant function. Its degree is 0, so that would be something like f of x equals 3. It's a constant function. It does not have a variable, and that is followed by the linear function. The linear function you'll probably recognize, f of x equals ax plus b. You see it often as mx plus b. Its degree is 1. And then quadratic functions have degree 2. They are ax squared plus bx plus c. And we are going to focus the rest of our lesson talking about linear and quadratic functions exclusively. So linear functions, you'll recall that they represent lines that have a rate of change that we call the slope. That rate of change is the slope. We call it little letter m. It's the rise over the run, change in y over x. And you recognize most of this stuff up here. The thing you might not recognize is the last thing on the right. And that says to calculate the slope, you plug in b into your function and get your output, and then subtract a's output, and then subtract or divide that by b minus a. So as far as a verbal description or characterization of linear functions, they are degree 1 polynomials. Their equations are f of x equals mx plus b or ax plus b, where m is not 0. Graphically, they are lines that have a slanted slope, and they have a y-intercept of b. When the slope is greater than 1, it's an increasing function, or excuse me, when it's greater than 0. If it's less than 0, then it's a decreasing function, and it has a y-intercept of b. So let's go ahead and jump into an example problem where we can model a linear function. And this one says we have a table that shows the relationship between the number of calories and the number of grams of fat in 9 different hamburgers from various fast food restaurants. Find the linear regression model for this data. So to do that, we're going to use our graphing calculator. And what I want you to do is to go ahead and be able to put all of that data into your lists. So you're going to use stat and we want edit there, so we just want to hit enter. And you can see I've already listed, under list 1 I've got the calories, and list 2 I have the fat grams, which is what we wanted. Then the next thing you're going to do, once you have that data already into your list, I want you to go to, let's see, I want to tell you this correctly. So we are going to go to, I believe it's the vars button. Let's check that out. Vars, and let's check statistics, which is option 5, and then equation. So move over to, and there's regression equation. You can hit enter, and it has entered your regression equation. If you would like to see what that looks like, you can hit Y1 on your graph, and it has entered that equation into your Y1 function. So your function, your linear regression model, is y equals, and let's bring that back up here for a second if it'll let us, y equals 0.071 x, so this whole long string of numbers is your slope, and then minus 9.268. So let's go ahead and write that. Y equals 0.071 x. Let's go to 3 decimal places. Plus, whoops, it was plus a negative, so it was minus 9.268. That's a point, not thousand. Okay, so that is what our equation looks like. So once we have the linear regression equation, then it says, according to your model, how much fat is in a hamburger with 475 calories? So what we want to do now is we want to calculate how many calories, or excuse me, how many fat grams there are in a burger with 475 calories. So what you can do is go to yvars, and so go to vars and then move to the right. We want yvars, and it says function, which is what we want, and we want to choose y1. Once you have that, just use a parenthesis and then put in 475. So what we're doing is we're finding f of 475, and this should give us an answer. So right there we see that if you have a burger with 475 calories, it should be 24.651 fat grams. So let's go ahead and write that, 24.651, right here, 24.651. So that was f of 475. Gave us that answer. So it says, in the context of this problem, what does the slope mean? Well, our slope right here is actually the ratio of the number of fat grams to the number of calories. So the slope is equal to the grams of fat per, I'll just write per calorie. So that's what that means in this problem. All right, quadratic functions and their graphs. So quadratic functions, you should be familiar with 2 different forms of quadratic equations. The first form here, which is a little bit more difficult to put it in this form, but if you see it in this form, it's easy to tell how to graph it. This is called the vertex form, and it's a parenthesis x minus h quantity squared plus k, where hk is the coordinate of the vertex. The other form that you will see is ax squared plus bx plus c. And the standard form actually comes from expanding the vertex form. So if I were to expand this right here, x minus h times x minus h, and use FOIL on that, okay, I would get x squared minus 2hx plus h squared. So just using FOIL right here, and then distributing the a through the parentheses, we get this. So we could say, if you look at the forms, we still have our ax squareds here, but b is equal to negative 2ah. So this is how we can solve for h. If I say b equals negative 2ah and solve that for h, I get h equals negative b over 2a. That is actually the vertex, or the x-coordinate of the vertex, and also the axis of symmetry of our quadratic equation, or of our parabola. And if we actually plug that value into the function, what we get out would be the y value. So graphically, when we're dealing with quadratic equations, here's what we have. So we're talking about this axis of symmetry stuff. That's the dotted line. The axis of symmetry is the point where the parabola is symmetric on both sides, where it's a reflection line, and it's a vertical line always. And so instead of h, we often say it's x equals negative b over 2a. And when we have a coefficient that's positive in front of our x squared term, the parabola opens up. If it's negative, it opens down. So that's what's going on with our quadratic functions. So let's go ahead and look at a couple of examples here. It says find the vertex of the quadratic function, then graph the quadratic function. Well, what's the parent function of this? By now, with our graph transformations, you should recognize what's going on here. The parent function is the quadratic y equals x squared. And we have a couple of graph transformations here. The 3 represents a vertical stretch of 3. The negative 2 is outside the function, so that's going down 2. The 5 is inside the function, so it's going left 2. So those are the graph transformations. So from that, you should be able to graph that. We know that the vertex then is negative 5, negative 2, based on what we just said with our graph transformation. So if we go left 5 and down 2, we should be able to graph that vertex. And then using our vertical stretch, we can go right 1 up 3 to have that slope of 3 to get another point, or left 1 up 3. And then we can go ahead and graph the parabola. Here's another example. F of x is 2x squared minus 6x plus 11, and graph it. Find the vertex. Well, on this one, our axis of symmetry, remember, is x equals negative b over 2a. Now, b and a are just the coefficients in front of the numbers. So for us, that's going to be negative, which is the opposite of negative 6, over 2 times 2, which is 4. So this is going to be a positive 3/2. So that is our axis of symmetry, and that is also the x-coordinate of the vertex. So to find the vertex, we need the y value at that point, at x equals negative 3/2. Oops, did I miss a negative in there? The opposite of negative 6, which is positive 6. I think I have a typo in there. I think it's positive. Yeah, that should be a positive 3/2. So disregard that negative sign in there. Scribble that out if I can there. So at positive 3/2. So let's go ahead and plug that into our function. So we want f of 3/2 is equal to 2 times 3/2 squared. I'll put that in a different color so we can see 3/2. And we're going to square that. Minus 6 times that same value plus 11. So let's go ahead and put 3/2 in there again. So then let's go ahead and expand this. So 3/2 squared is really 9/4, and that's multiplied by 2. And then we're going to subtract 6 over 1 times 3 over 2, and then we're going to add 11. So let's see, 2 we can simplify here, and we get 9/2. This one we can simplify here, and we get a 3. 3 times 3 is 9, so it's minus 9 over 1, and then plus 11 over 1. Well, this is actually just plus 2, and so we have 9/2 plus 2. Well, 9/2 is 4.5, plus 2 is 6.5, which is the same as 13 over 2. So our vertex is actually the point 3/2, comma 13/2. So if we wanted to graph that, 3/2 is really 1.5, and then 13/2 is 6.5. So we go right 1.5 and up 6.5. 1, 2, 3, 4, 5, 6.5. And we can graph that point right there. So there is what our parabola looks like. Since it's a positive 2, it's going to open up, and that is your graph. Example 4 says the Welcome Home Apartment Rental Company has 1,600 units available, of which 800 are currently rented at $300 a month. A market survey indicates that each $5 decrease in monthly rent will result in 20 new leases. So some significant information here. I'm going to underline this a little bit for us. And it says each $5 decrease in monthly rent will result in 20 new leases. So that's a significant piece of information for us. Determine a polynomial function, r of x, that models the total rental income, where x is the number of $5 decreases. So that's another important piece there. X is the number of $5 decreases in monthly rent. Okay? So our function r of x stands for revenue. So our revenue is basically going to be the number of rentals multiplied by the cost per rental. Okay, so that's how much money we bring in, however many apartments we're renting, and how much we're charging for each. So in this example, we are going to be looking at, right now we have 800 of them are rented at $300 a month. But we're talking about getting some new leases with every $5 decrease in rent. So we're going to be varying that a little bit. So 800 are rented, but we're going to get 20 more for every $5 decrease. So if we had one $5 decrease, we'd get 20 more rentals. Okay, and then on the other side of the equation, the cost per rental, right now we're charging $300, but that's going to go down by $5 for each decrease. It says x is the number of $5 decreases. So that is actually the model we're looking at. If we use FOIL and expand that, we get that quadratic equation. So that is an expression right there. It's a polynomial function modeling the total rental income. That answers the question that we were asked. Part B says find a graph for the rent levels between 175 and 300 that clearly shows a maximum for r of x. What rent will yield the maximum monthly income? Well, these numbers that they are giving you right here, 175 and 300, where this comes from, if we don't reduce any rent at all, that corresponds to 0 x's. And if we do 25 $5 decreases, 25 times 5 is 125. And if you subtract 125 from 300, that gives you the 175. Okay, so finding the graph between these levels, that's telling you let your x values be between 0 and 25 in your graph. Okay, so I went ahead and did that on my graphing calculator. I put in this equation into y1, and I graphed it, and you're going to have to mess with your window because your y values are huge. Okay, I went from like 200,000 to, I don't know what I went to, 300,000 possibly. And so I got this section of my graph that I could see where there was a maximum value. And I just did a second calculate on the calculator, and that maximum value occurred at x equals 10. And x equals 10 corresponded to $250,000. So it said what rent will yield the maximum monthly income? Well, when x is 10, that means 10 $5 decreases. So we're really decreasing $50 from where we're at now, which was 300. So the new rent is $250 a month. So as a summary of our quadratic functions, verbally they are polynomial equations of degree 2. Algebraically, there are two formats. You might see the standard format, or you might see the vertex form. So standard form and vertex form. Graphically, they are parabolas. If a is greater than 0, it opens up. If a is less than 0, it opens down. They have y-intercepts of c, and the x-intercepts you can find using the quadratic formula. We'll probably use our graphing calculators for the most part to find the x-intercepts. That's where it crosses the x-axis when we do that second calculate intercepts, or there's various names that we've called that. So it looks like that's going to do it for this lesson. We'll see you next time.